Thank you very much, Sasha. It's a real pleasure to be back at MIT. This is my first time back not being a PhD student. As Sasha said, I was advised by Philippe Rigolet. He's also a joint author on this work. And originally, I wasn't sure that Philippe was going to be able to be here for this session, so I wanted to remind you what Philippe looks like if you haven't seen him. Oh. My computer is frozen, so you won't be able to.
What you get for saying this thing.
Yeah, exactly. Right? It's like a. OK, that's what Philippe looks like. If you ever want to know what it's like doing a PhD with Philippe, just imagine him staring into your soul like this. It's very, it's a real bracing way to get a PhD in mathematics. OK, so as I said, I'm going to be talking about this estimation of Wasserstein distances in the spiked transport model. I don't expect any of these words necessarily to be comprehensible at the moment, but the talk will naturally fall into two pieces. The first, I'm just going to tell you about this general problem of estimating the Wasserstein distances. What does this mean? What are the things we know about it from a statistical perspective? What can we hope to accomplish? And in the second part of the talk, I'm going to describe a new model that we think is interesting that maybe helps to illuminate some of the finer-grained difficulties of estimating the Wasserstein distance and shows you the interplay of low-dimensional structure in high dimensions. And the key through all of this is the idea that we're going to be interested in how to alleviate the curse of dimensionality for these high-dimensional statistical problems involving optimal transport. So what is the problem of estimation of Wasserstein distances? Let's suppose that I have two probability measures that live in RD. And I would like to know what is the Wasserstein distance between them. OK, so many of you may not know what this object is. I'll say what it is in a second. I'm not in this talk going to really motivate why one would want to know the Wasserstein distances between distributions in the first place, but it's a natural measure of distances between distributions, and it's proven useful in a lot of tasks involving image analysis, involving high-dimensional geometry, and different types of statistical problems with geometric structure. But if you want to do anything with it, at the very least, you need to be able to compute this thing, the Wasserstein distance between two probability distributions. So what is this? Let me just briefly remind you, for those of you who haven't seen this definition before. So the Wasserstein distance, in its simplest form, you can write down a definition that looks like this. The idea is that I'm going to try to measure the distance between two probability distributions that live in a metric space by asking how cheap or how expensive it is to transport one distribution into another. So I have two distributions in my hand, call them P and Q. And what I would like is some map that picks up every little bit of P and brings me to Q and makes the expected distance that I travel as small as possible. So I want to make this map T take me from P to Q, but do it in a way that's cheap. I don't want to have to move a bunch of mass really long distances. And so this definition was proposed a long time ago by Monge in the 18th century. And it's really the starting point for the whole theory of optimal transport. One subtlety, and I'm not going to spend too much time on this today, but something to note is that the definition of optimal transport in this case is not exactly right. So this was the definition proposed by Monge, but it's not a very good definition because this problem here of finding a map T that takes me from the measure P to the measure Q might not be valid at all. There might not even be a feasible map that does this thing. So the more familiar definition just asks, instead of a map, just for a coupling. So I'm going to try to construct two random variables, x and x prime. Marginally, x has law P, and x prime has law Q. And I just want these random variables in expectation to be as close as possible to each other. And if I say this, then I've defined what's known as the Wasserstein distance. So this is a bona fide metric on the space of probability measures on RD. And this is sort of the L1 version in the sense that I'm just taking the expectation of the norm. I can define the whole family of Wasserstein P distances by looking at the expected Pth moments of this quantity. Oh, that's not what this slide says. This slide says, so there's the Pth moments of this quantity. So I'm just taking the expectation of the distance to the P. And this is a list of names of people who have thought about this. So Monge was the one who proposed it originally. Kantorovich is responsible for this modern reformulation in terms of couplings early in the 20th century. And some modern names who have thought about this from the perspective of geometry and PDEs are everyone's two favorite recent Fields Medal winners, Villani and Figali. So, okay, this is an object. This is a notion of distance between two probability distributions. You hand it to me and you ask, can I compute this thing between two distributions? But of course, if you are like me and you are interested in statistical questions, this isn't even the right question either. I'm not interested necessarily in the abstract problem of how to compute Wasserstein distances between two populations, mu and nu, but I actually see samples from these distributions, right? I see IID copies of random variables distributed according to mu and according to nu. And my job as the statistician should not be so much to ask, can I actually just compute the Wasserstein distance between these two distributions, but can I estimate it on the basis of data? So if you give me IID samples from mu and IID samples from nu, can I estimate how far or close they are in the Wasserstein sense? And that's going to be the goal of the first part of this talk. I have IID samples, and I just want to know how close the underlying distributions are. And in particular, I want to have quantitative bounds on how many samples I need in order to get a meaningful estimate of this quantity. How big must n be in order to get a good estimate for the Wasserstein distance between these two distributions? So what should we try? Here's a first attempt. One thing that I can certainly do is just say, well, you've given me IID samples. I can package these up, if I like, into empirical distributions, right? Just take an empirical distribution that assigns mass 1 over n to each of my samples. And I can ask, maybe if I just drop these into the definition of the Wasserstein distance, maybe this quantity is close to the Wasserstein distance between the underlying measures. If so, I'm done. I don't have to do anything clever to estimate this quantity at all. The problem is that in general, this is not true. It's not the case that these two things are close to each other. The problem is high dimensions. If the dimension is low, maybe it's not an issue, but it's been known for a long time that if my measures are d-dimensional in some sense, say they live in Rd or on a d-dimensional manifold, then the typical distance between these two quantities is no better than n to the negative 1 over d. So I have these high dimensional distributions. D is something huge. I need a number of samples exponential in the dimension in order to get anything that approaches the true underlying quantity that I hope to estimate. So this is the problem from our perspective. Is there anything that we can do to make this rate any better? Maybe by some other idea. So that's what I mean by the curse of dimension. Is there anything we can do to avoid this rate? Before I continue, any questions about what I've said so far, about the definitions or about what the goal of the problem is? Okay.
You only have sample access to this.
Only have sample access to the distribution. Yep, IID samples is the only thing that I got. So there are two possible paths forward, we might imagine. One is maybe my strategy of just using the empirical measures was dumb in the first instance. Maybe there's a smarter thing that I can do in order to try to estimate this quantity. Or maybe it's the case that the problem that I gave myself was too hard to begin with. And then if I assume some extra structure, that it's possible to do this at a better rate, if I assume some structure that I think is reasonable in practice. So what we're going to see is that the answer to the first question, whether I can do anything smarter, is essentially no. There's not really anything better than this rate in order to estimate Wasserstein distances between high-dimensional distributions. But the second part of the talk is going to offer one type of structure that can be exploited. Even though the distributions are high-dimensional, under some settings it's possible to estimate this quantity faster. And that's this so-called spiked transport model that I'll talk about in the second half. So what are smarter strategies we could possibly adopt? Let's try and understand the set of possibilities here. So this was the procedure that I advocated at the beginning. Let's just take my samples, drop them into the definition of the Wasserstein distance, and see what happens. Why is this not going to work so well? Well, the problem is that if I start with some measure mu that's absolutely continuous with respect to the Lebesgue measure, then in general, mu and mu n are super far apart in the Wasserstein distance. Even if I just look at the distance between mu and mu n, this object scales like n to the negative 1 over d, almost surely. So it's just a statement about the fact that a discrete distribution, mu n, cannot well approximate the underlying distribution mu. And this is the fundamental reason why dropping these probability distributions that are just formed from your IID samples never gets you a rate better than n to the negative 1 over d in general. But of course, there's no reason that I have some points here. There's no reason I can't do some other thing with the samples, like maybe construct some better proxy measures. You know, put my samples into some definition that spits me out some mu tilde or nu tilde, and ask, maybe it's possible to construct such a mu tilde that's much closer to mu than this lower bound would have us believe. And it actually turns out that this could work. I'm not going to talk about this much today, but if I assume, for instance, that mu has a smooth density, you can actually do something better than just using IID samples by doing some smoothing. So this was a phenomenon that was noticed in the case of W1 by Tengyuan. I'm not sure if he's still here, Tengyuan Liang, and then some other work of Singh et al. And then we also did some work that involved this for the WP case. But in general, this is saying, OK, if you have smoothness, yes, there's a better proxy measure that you can compute. But it's the case that in general, this is not possible. So if I have extra smoothness, I can smooth in order to get some better approximation. But there's a strong lower bound due to Singh and Potros from a few years ago that says that if the name of the game is trying to compute some proxy measure, mu tilde n, there's never anything I can do that will successfully manage to get closer than n to the negative 1 over d in general. So this is a minimax lower bound, saying that there's no procedure that's going to work over all possible choices of mu that live in my space. So if my strategy is going to be compute a proxy measure and then compute Wasserstein distances using that proxy measure, this lower bound says that can never do anything better than n to the negative 1 over d. Questions on this so far?
Is this lower bound saying that I can construct two measures or two distributions over measures so that from this many samples you cannot tell up?
So great. That's not what it says. What the lower bound I'm about to present will say that. This says something weaker than this in the sense that it's asking you to do a stronger task. It's not merely asking you to tell whether these things are close together or far apart. It's asking you to actually construct, it's asking you to estimate the distribution in Wasserstein sense rather than just estimating distances between distributions. So this is a very important point that, that I'll come back to in a second. Basically,
The rates are different, you're saying?
well, I conjecture the rates are the same, but we don't know yet. So yeah, Kostas brings up exactly the right question, which is I am implicitly trying to solve a harder problem here in the sense that I have asked to construct distributions that are close to my underlying distributions in the Wasserstein sense. But it may be possible that just estimating the distance, which was my original task, is easier than this task, right? And the whole field of sublinear algorithms, especially in the computer science community, knows facts like this for different notions of distance between probability distributions. So this is not an unknown phenomenon for other types of measures like TV or chi-square divergence or KL or something like that. So a priori, it's possible that I can do something smarter with all of my samples that serves as a better estimate for the underlying distance, even if I can't estimate the distributions themselves. OK, and this is the thing where I actually, to Kostas's point, I don't know the answer to the question of whether there's anything fundamentally better to do here. Before our work, as of a couple years ago, the best lower bounds I know for this problem were due to a group of people at MIT, actually. So Ronit Rubenfeld and some students proved a lower bound of the following form, that if I'm interested in estimating W1, at least, and I confine myself to, say, the unit cube, the unit hypercube in d dimensions, then the best I can do is a rate that looks like this. So to put this in sort of sample complexity language, if you're more used to that from the computer science side, it says that I need a number of samples that's like epsilon to the negative 2d over 3. So this is a worse lower bound than we hope to prove, because we conjecture on the basis of the naive thing that the optimal rate here would be something like 1 over d rather than 1.5. So this was the state of the art, that a lower bound of this form that this form existed, where there's still a relatively large gap from the upper bound that we know. Now we can say something better, which is that any improvement must be quite small, in the sense that the lower bound, instead of being off by a 1.5 to 1 factor, is off by at most a logarithmic factor, so that there's a lower bound for estimating the WP distance of order n log n to the negative 1 over d. Very close to the n to the negative 1 over d. But this log n is interesting, and I'll say more about it in a second. I just want to flag also that Tengyuan independently had similar results for the W1 case, using different techniques and with a slightly weaker bound. But the qualitative story is the same. Both of these bounds are off by some logarithmic factors, off the naive rate you would expect of n to the negative 1 over d. So what this lower bound is saying is that up to this log factor, estimating the distribution itself and estimating the distance are about as hard as each other. But whether this log factor is actually present is an interesting question. I'll say more about that in a second. But any questions about this claim? Yes?
What you say is that you know to prove this bound, but you don't know what estimators can achieve this bound.
So I know no estimator can do better than this. But I don't know if there's an estimator that actually achieves this rate, this n log n to the negative 1 over d. Whereas I know a trivial estimator that gets to n to the negative 1 over d, which is just dropping the empirical measure. Right. So that's the open question that I don't know the answer to. Is there an estimator actually achieving this improved rate? Any other questions about this claim? I'll say some words about the proof. Yes, Inho?
D-dimensional metric space, you mean the covering numbers?
Yeah, I mean, let's assume I mean in this case just Minkowski dimension, upper and lower Minkowski dimension d. Yeah.
So how does this relate to L1 distance?
Great. So I'm about to say, so the proof technique uses crucially what's known about estimation in L1, where this log n factor is a quite deep fact. So yeah, I'll say that right now. So as Kostas correctly intuited, oh, these slides are backwards, doesn't matter. As Kostas correctly intuited, the first question to ask is, can I leverage anything I know about total variation distance estimation, L1 norm in other words? There's been a wonderful series of works inaugurated, I guess, by Greg and Paul Valiant. Yi Hong and his student Pengquan Yang have good work about this. And then a group of students of Tsaki Weissman at Stanford have worked on sharp rates for this problem as well. There's a lot known about estimating total variation distance between distributions, discrete distributions. And that is a nice structure to work with because the L1 norm is totally unstructured. It's totally symmetric. All of the things that matters are just what mass is at what place. So let's see if we can leverage this in our context. So I said I wanted to start with some d-dimensional metric space, X. Let me first try to use what I know about discrete distributions by just putting some separated set inside X of points. And I'll just assume that my distributions are just supported on these points. Now, if these points, if my measures are supported on this delta separated set, then I have a lower bound of the following form. I get control over the Wasserstein distance via control over the total variation. So why is this? So we know that the total variation means this is an infimum over all couplings, and it just asks to make the probability that 2 points differ as small as possible. But whenever 2 points differ here, I have to pay delta to the p in order to bring one to the other. So this norm, which is like delta to the p scaled of the trivial norm, is a lower bound for how far I'll have to move things in the case of the Wasserstein distance. Because I have to move stuff a certain amount, and every time I move stuff, I pay delta to the p. The problem is that this control is far too loose, because the only upper bound that you can write, if you wanted to actually control the Wasserstein distance in terms of the total variation, is this trivial upper bound. Right? So I also have an upper bound that says whenever I move mass, if my total set has diameter 1, then, okay, the amount that I have to pay to move it is always less than 1. So one has an upper bound of the following form. Neither of these bounds is improvable in general, and they're off by a factor that's way too big for us, right? Because delta is going to be something really small. So this sort of sandwiching by total variation is not going to be strong enough to allow us to extract any lower bounds just from the total variation distance alone. The trick, it turns out, is to do this embedding in a slightly more careful way. So what we're going to do is we're going to start by measures that live on just m atoms somewhere else. Right? So I define two measures that live on m atoms. Q is some probability distribution that lies in the m-dimensional simplex. And I'm going to let U be the uniform measure on this set. In order to embed these into space, I'm going to split up the atoms, split up the support, and randomly embed them in my space using a uniform random permutation. And if I do so, what one can show is the following, that if I start from distributions up top and then randomly embed them in the space, then the bounds become significantly tighter. So the measures that I construct that lie in my metric space, we again have a lower bound of the following form. That's exactly the lower bound we had before. And the upper bound is close. If I cover up the orange stuff, the upper bound is exactly what I would like, but it's not. There's a fudge factor. I see a fudge factor that involves the chi-squared here, and I get a different power on the total variation. But the point is that if I am in a regime where the total variation is constant and where the chi-squared is constant too, then these two sides are of the same order. And then I can use what I know about estimating total variation distance in order to say something about the Wasserstein distance problem. And the last piece of the puzzle then is to provide exactly the sort of claim that, that relates to these, relates difficulty of distinguishing distributions to the bound that I put right here on the top of the slide. Namely, I need to come up with priors that satisfy the following types of requirements. Two sets, pi 0 and pi 1, that are, one is close to the uniform distribution, the other is far from the uniform distribution. All of them are close enough in chi-squared to the uniform distribution. And these two sets are hard to distinguish if the number of samples is not too large. So this proposition is very much along the lines of what was developed earlier by Greg and Paul Valiant, by Yi Hong and his student. The problem is that if you look at their constructions, one can check, and by one can check I mean I had to spend time checking, that their constructions do not satisfy this third requirement. The constructions that are used in these lower bounds for TV have chi-squareds that blow up. So one has to construct slightly different priors that also keep this quantity controlled. But putting this all together, one gets the claimed result, which is that any estimator, W hat, is bound to incur something that's almost n to the negative 1 over d, perhaps up to this log factor. It's a very interesting and fundamental question whether this log n is present. So in the case of many different types of distances between distribution, Philippe is fed up, many different types of distances between distribution, say TV, chi-squared, KL, and a number of other quantities related to distributions that are symmetric, it's known that there's always a log n factor to be gained in those settings, meaning that the naive thing and the optimal thing are off by a factor of log n. This is a phenomenon that's been dubbed sample size enlargement by that group from Stanford. And so it's an interesting question whether the Wasserstein distances exhibit this type of sample size enlargement as well, where you can actually gain this log n factor. I conjecture the answer is no, because the difference, the key difference here is that the Wasserstein distances are strongly not symmetric with respect to relabeling of the points. But of course, my construction that I used involved IID random permutation, so I symmetrized it myself, which is why my construction necessarily, I think, is not really picking up on what actually makes this problem strictly harder than the corresponding problems for TV and chi-squared and KL and so on. However, the ease of analyzing those other things comes from the symmetric IID nature of the problem. So coming up with a stronger lower bound here seems to require some new ideas. So, okay, suppose that you're not a theorist and you don't care about this log n factor. Then it still seems as though we might have an issue in the sense that these two rates both seem to say that we have to pay exponentially in the dimension to do any non-trivial estimation of the Wasserstein distance. So we can ask if there's anything we can add, any more structure we can add to the problem that will help us. So there's a line of work in the sort of applied optimal transport community that just closes its eyes to this problem and decides to just try to solve a lower dimensional problem instead. So there's a number of different proposals that go under different names, but these basically say high dimensional distributions, you don't want to deal with them, compute Wasserstein distances of some low dimensional projections instead, and hope this is a good proxy for the thing that you actually care about. It's not clear, though, that this is a meaningful or principled thing to do in general, and it was not clear whether there's a statistical model where you can show that such things are actually reasonable, giving you improvements over the rates that you could get from just the naive proposal. So our second goal was to find some structural assumption on the measures under which this is actually a reasonable or interesting approach. And we took our inspiration here from an extremely influential line of work in statistics, which started with a paper by Ian Johnstone in 2001 on what's known as the spiked covariance model. So Johnstone looked at some real-life data. This is data from a phonemic data set. So it's taking recordings of people speaking English, and it's trying to extract features from those recordings. And what's plotted here is a so-called scree plot. So we have here the empirical covariance matrix. They look at the spectrum, and this is the size of the eigenvalues against the rank. And so the empirical observation from this paper was, look, a lot of real-world data looks like this. There are some directions that seem to matter a lot, some spikes, and some stuff that seems to just be noise, who cares, whatever, the bulk. And so Johnstone set out to write down a statistical model under which one could prove things about data that looked like this. And he proposed what's now known as the spiked covariance model. So the idea of the spiked covariance model is start with your high dimensional distribution, so like an isotropic Gaussian in RD, no preferred direction, there's no interesting structure there, but it is a high dimensional distribution. And let's plant some low dimensional structure by assuming that the covariance has the following form: identity plus some rank 1 spike in some certain direction. And then the question in that community is, can I estimate this? Right? Can I find the spike? Can I estimate the magnitude of beta? And so on. But the key takeaway from this picture is that it's a low dimensional perturbation to a high dimensional model. It starts off with some high dimensional distribution, and it plants some structure that lives in an unknown low dimensional direction. And it tries to ask, to what extent can this be exploited? So in the context of optimal transport, we propose the following generalization of this model, which we call the spiked transport model. So here's the idea. One way to think about what's happening in the spiked covariance model is that I'm looking at one direction and I'm changing some second moment information in that direction, right? I'm changing my Gaussian from a Gaussian with variance 1 to a Gaussian with variance strictly bigger than 1. But all the other directions I'm not touching. So we say something similar here. We say start with a high dimensional distribution, some whatever you like. And now imagine that the second distribution differs from that one only along a low dimensional slice. But the remaining directions are still the same. So formally, what I'm going to require is that I have independent random variables, x, y, and z. Z is my noise directions. These are the ones that I don't touch and I haven't done anything with. X and y are allowed to have any relationship that I like, but they're supported on a low dimensional slice. So informally, this is the picture. I have high dimensional distributions. These are purple, but the relationship between them is low dimensional. I've perturbed them along some low dimensional direction. And this is the question. Under this sort of assumption, when my measures are truly high dimensional, is it any easier to estimate the Wasserstein distance between these two things from a statistical standpoint? Can I get away with fewer samples than I could in the totally unstructured case? And here the answer is yes. So what we show are rates of the following form: that if mu and nu satisfy some conditions, then under the spiked transport model, I can come up with an estimator that has behavior of the following form. So what do I pay here? I have n to the negative 1 over k plus a term that's like root d over n. Interpret the first term as just the rate that I would have to pay even if the subspace were known in advance, right? Even if I were just focusing on this k-dimensional slice where all the action is, this is what I would need to pay in order to estimate Wasserstein distances on that slice. The second term is the price to pay for the fact that I have to look over all possible directions, right? The fact that I don't know which direction this thing lies in. So we see two terms here. We have a term that pays for the k-dimensional slice, and the only appearance of the ambient dimension is in this second term, polynomially in n. And both of these terms are optimal up to log n factors. I can't do anything better than linear, like this root d over n, I can't do anything with. And we already know that paying something like n to the negative 1 over k is mandatory up to log factors if I want to estimate the Wasserstein distance. The same thing works for general WP. I can play the same game, and I get basically the same story. No. Any other questions? Okay, so I have to say, having left MIT 6 months ago, I am a little disappointed because MIT people are usually very aggressive. And I expected at least someone to make me say something about what these some conditions are. Because, you know, I don't want to get out of this talk entirely unscathed. Normally, I would like to hide conditions because, you know, who likes spurious conditions? But today I want to talk about this condition because I actually think it's very interesting on its own and sort of cute. The assumption that we are going to require on mu and nu is that they both satisfy something that's called a transport inequality. What is this thing? And why the heck does it matter for my particular setting? So transport inequalities were proposed, originally developed in 2 different communities by Martin and Talleyrand in order to solve problems involving concentration of measure. So Martin, she was interested in Boolean space. Talleyrand was interested in Gaussians. But they both had questions about the way that tensorizing these distributions behaved when it came to high-dimensional concentration of measure questions. And this is what they both proposed, an inequality of the following form. So we'll say that mu satisfies the transport inequality Tp if the pth Wasserstein distance can be controlled by the relative entropy, the KL divergence. So I ask here that for any other measure pi, the Wasserstein distance is at most the square root of the KL divergence up to constants. Now, why does this assumption, let me just say a word about how to interpret these in more familiar terms. Sub-Gaussianity is basically equivalent to satisfying a T1 inequality. And a T2 inequality is implied by a log Sobolev inequality, and in some cases the implication works the other direction as well. But these are both connected to common understanding, things that people understand in the world of probability theory. So why are these connected in any way to the problem that we're solving? Well, one thing that you might have thought of when we were looking at this high-dimensional distribution, I was looking at low-dimensional projections. You might ask that we would need probably some quantitative control over how well Wasserstein distances concentrate, right? So I have some Wasserstein distance in high dimensions. If I'm going to make it the case that I can pick something out in a high-dimensional space, if you've proved stuff like this before, you will want to have some concentration property for Wasserstein distances. And so the key fact, which I think is really amazing, is that for p between 1 and 2, a transportation inequality is equivalent to the concentration of the Wasserstein distance. So let me just say that this statement of the theorem we could not find exactly in the literature, but I don't want to take credit for it really because Gosselin and Leonard really developed these ideas themselves. We wrote this down, but this already exists in some form. But here's what's interesting here. It's not surprising that if I tell you it satisfies some inequality that's connected to log Sobolev inequalities, blah, 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 whatever, that this thing will concentrate well. Sure, fine, I believe it. What's remarkable is that the single concentration of this function implies a TP inequality. So if I know that I have sub-Gaussian tails for the Wasserstein distance, I automatically know that the distribution satisfies a general geometric inequality of this kind.
So you need to satisfy TP for all P?
No.
Or for any?
Fix a P.
Okay. Oh, it applies for any P.
If this holds, then this holds, and this holds, and this holds. Okay. Only between 1 and 2, we can say for now. The implication goes the other way for P greater than 2, but we don't know the equivalence. But yeah. For fix a P, mu satisfies TP if and only if WP concentrates in this way. The proof, which I want to emphasize is due to Gosselin and Leonard, is amazing and fits on one slide, and so I'm going to show it to you. And I'm only going to prove this direction. Like I said, I don't think this direction is that interesting or surprising. If I satisfy a TP inequality, I get concentration, sure. But I'm going to show you why concentration implies a TP inequality. The proof is actually based on large deviations arguments, surprisingly enough. So here's the proof. Let me define the following set. I'm going to look at all measures pi that lie outside of a Wasserstein ball around my starting measure mu. It's a particular set of probability measures. Now, Sanov's theorem tells me that I have the following large deviation behavior. That if I want to understand this large deviations event, right, where I look at the probability that the empirical measure lies in this set, it just depends on this KL projection on this other side, right? It depends on the closest point to this set in the sense of relative entropy. So this is Sanov's theorem. Let's parse the right-hand side. Remember what I assumed. I assumed that this quantity concentrated well around its expectation. In particular, had sub-Gaussian tails. So this probability then, I assume can be bounded by something that's of sub-Gaussian form. So plugging it in, I have to correct by subtracting out the mean, right? Because I had concentration around the mean. But once I subtract out the mean, then this probability, by assumption, can be bounded by this quadratic thing. Okay, now I take the lim sup as n goes to infinity. The only thing that changes is this expectation term dies, because this thing converges to 0. So all that's left here is just minus t squared over 2. So what have we shown? We have shown that if the measure pi lies inside this set, in other words, if the Wasserstein distance is greater than p, then the relative entropy is at least t squared. But now we're done. Because this implies that for any epsilon greater than 0, this thing must be smaller than this thing, right? Just by choosing a t that's an epsilon smaller than the quantity that I care about. So this large deviations argument automatically gives us that the concentration of this one function implies an inequality of this form. So to go back here, the reason that we needed this assumption, right, is because we need to assume some concentration of the Wasserstein distances in order to prove our claim. So we can assume exactly the concentration we need, and it turns out that that assumption on concentration is exactly equivalent to these measures satisfying a transport inequality. Okay. Everything seems good, maybe, but seems like we've gained a lot. We have this low-dimensional structure. My sample complexity has improved a ton. The only last detail is to figure out how to compute my estimator. So what is this estimator that I propose? Well, it's the simplest thing in the world. I'm just going to look at all k-dimensional subspaces of my measure, project my empirical measures to this k-dimensional subspace, and look for whichever subspace gives me the largest Wasserstein distance. So search over all possible subspaces, just choose the one for which the Wasserstein distance is the biggest. Well, now you're worried, because this seems very, very, very bad indeed, right? Souping over all k-dimensional subspaces does not seem like a profitable, practical algorithm. So, okay, I have nice statistical rates, but for an estimator that I can't compute. So we need to ask, is there anything we can do that's computationally efficient? Right? The estimator that I just proposed did not seem easy to compute. Is there something I can do that is easy to compute? Well, in a certain special setting, you can do something. So you can put together some stuff that already exists in the literature to get some type of result. So there's this work on something called the Gaussian ICA problem, independent component analysis, that's been studied in a number of communities. But Vempala and Xiao first noted that if you're in the special case where mu is a Gaussian, you're starting from Gaussian measures, and you're in this spiked transport setting where the non-Gaussianity lies on some low-dimensional slice, then if mu and nu differ in a low-order moment, then I can find the slice, find the spike with a polynomial number of samples in polynomial time. Right, so if I have something that differs from a Gaussian in a low-order moment, say that my transport changes the 5th moment of my distributions, then I can find this via a polynomial efficient algorithm, maybe with poly d samples, not necessarily the exact right constants, but with something that's polynomial. Okay, this says something about low-order moments, but we were interested in perturbations with respect to the Wasserstein distance. But you can say something quantitative about the moments, how the moments must be affected by a perturbation in the Wasserstein sense. So it turns out that if I have two sub-Gaussian measures, and they differ in their Wasserstein distance by some amount, then I can find a relatively low-order moment where the difference is relatively large. I stress that this relatively large is extremely weak. Unfortunately, it's not possible in general to improve this exponential gap between these two things. But if I have some separation here, I have some low order moment at which these differ. And putting that together, I mean, these two results that already were out there, you get as a corollary the weak type of guarantee that if mu and nu are really far apart, and mu is a Gaussian, then I can find the spike in polynomial time. Because if they're really far apart, then there is some low order moment that differs by a constant amount. And then Van Pala and Xiao's algorithm shows me how to find it. However, we conjecture that once I don't insist on this sort of strict separation, that no computationally efficient estimator exists. We have evidence in the form of what's known as a statistical query lower bound that says that at least, even if I'm in a Gaussian, so I have a known base measure that I'm comparing to, if I allow my distance to be as small as 1 over root d, then even detecting whether there's a spike or not requires at least an exponential number of queries to a statistical query oracle with exponential precision. So if you're not familiar with SQ lower bounds, you can ask me afterwards. But this is a type of evidence that algorithms of a certain sort will need a lot of samples or a lot of computational time in order to actually find a spike. But note that this regime, this 1 over root d, our non-efficient estimator can find this spike with only a polynomial number of samples. So at least if you believe SQ lower bounds, it's reasonable to conjecture that there's no polynomial time estimator that achieves this optimal rate. So just to sum up here, I asked at the beginning, can we avoid the curse of dimensionality? At least without additional structure, the answer is no. This n to the negative 1 over d rate is nearly tight. Though there's an interesting open question about whether the rate is exactly n to the negative 1 over d or less by just a logarithmic factor. But I can assume some extra structure that at least statistically brings me a lot of benefits. So if I employ this spiked transport assumption, then I can estimate WP with far fewer samples. The problem, of course, is that we don't know how to do so in a computationally efficient manner, and there's reason to suspect that any such estimator that actually improves upon the naive rate needs exponential amount of computation time. Can't be done in polynomial time. And I think the interesting open question that's swirling around these things is exactly the one that met the development of sparsity as a ruling theme in statistics for the past 20 years. Sparsity in certain bases is really exciting because information theoretically it gives benefits, but we also know of relaxations in algorithms that can exploit sparsity in a computationally efficient manner. When it comes to these Wasserstein distances, I think it's still a little bit open what the right notion is of a structure that can be exploited both from a statistical and a computational perspective to get better rates. And that's it. Thank you all very much.